Welcome protein coders, let's build some coding muscles. Today we're gonna see bridges in a graph. What is a bridge in a graph? It is the edge on removal, the graph will split in two components. Okay, let's see with the example. So let's choose a random edge in the graph. Okay, now if I break this edge, will the graph will split into components? No, right? Because I can still reach these two nodes via some other path. Similarly, if I choose this edge, again it will be a same component, right? But what will happen if I choose this edge? I cannot reach these two nodes via some other path, right? So this is a bridge edge. Similarly, this edge also. So we have two bridges. So if you observe carefully, if we have a cycle in a graph and we remove an edge, any random edge, then we still have an option to reach these two separated nodes via some other path. That means in cycles we can't have bridges. So I can write edges which are part of a cycle can't be a bridge edge. Okay. Now let's see how we're gonna do it in more detail. So we have our graph here, okay, which has a cycle. So what we do here is we will take a vector called discovery time. Okay. This is the first time when we visited that node. So for node 0, if we start our DFS, the discovery time will increase in every step, right? So let's perform our DFS and increase discovery time at each step. Similarly, when we reach at 5, we found our cycle because 2 is not the parent and is already visited. So I know this 2 and 5 edge is not going to be part of our bridge. And when my DFS will trace back, I want to remember this node number 2. Okay, that till node number 2, when we are tracing back, all the edges are going to be the part of the cycle. Okay, for this, we will take a separate vector, low vector. Okay, this will store the discovery time of the lowest node which I have visited via this cycle. Okay, so let's initialize our low vector, and while doing DFS again, similar to DT, we will initialize our low, okay, for each node. Now when we reach at 5, what I will do is I saw a cycle. I saw a node which is not a parent and is visited. That means a cycle. So our DFS will trace back, but after coming back, what I will do is I will update the low of the node number 5, and the low will become the minimum of the low of 5 and discovery time of node number 2. That means I carried this discovery time of 2 with me while tracing back. Okay. Now, when I trace back from 5 to 4, I will check the discovery time of the node number 4 and the low of node number 5. Okay. So if dt of 4 is greater than the low of 5, that means I can reach this edge via some other path, the node number 5. Okay, we don't need this edge 4 to 5, so this can't be a bridge. Okay, I can write this can't be a bridge by comparing the discovery time and the low while tracing back DFS. Simple. Now similarly, then we will update this low of the node number 4, and this will become the minimum of low of node number 4 and low of node number 5. Okay, at first when we found out cycle, the low became the minimum of the discovery time of that node which we found out, comma low of u, right? But here we are taking the minimum of low of u comma low of v. Okay, similarly when we trace back, the low of 4 will become 2 and the discovery time of 3 is 3, which is greater than or equal to 2. So this edge will also not be the part of the bridge. Similarly, edge number 2 to 3 will also not be the part of the bridge because the discovery time is greater than or equal to the low of 3. But when we update the low of node number 2, it will become 2. Okay, minimum of 2 comma 2, so it will be 2. And you see discovery time of 1 is 1, which is less than the low of 2. Okay, so I can't reach any node previous to 1 via some other path. Okay, so this will be our condition to check whether a edge is a bridge or not. Similarly, the node edge between 0 to 1 will also be a bridge. Okay, if we compare the discovery time and low. Now, what steps we have performed? We performed the DFS and keeping a discovery time and low vector initially while going into the DFS, and while returning back, when we found a cycle, we will update the low and trace back. And while returning, we will check if the discovery time of U is greater than the low of V. That means I have reached the V earlier also. Then it means it's not a bridge. There is a cycle present, or else there will be a bridge. Now let's see in the code how we're gonna implement this. Let's first initialize our timer. Okay, vector int of discovery and low, vector boolean visited, a vector of int to store bridges. Now let's start our DFS. First mark the current node as visited. Okay, and we will assign the discovery time and low time is equals to the timer, and we will increase it. Then we will visit the neighboring nodes for int v in adjacency list of u. Okay, if v is the parent, then we will continue. We will not do anything, or else if the node is already visited, the neighboring node is already visited, that means we found a cycle. What we will do? We will just update the low of u with minimum of low of u comma discovery time of v, cycle found case. Okay, or else if it is not visited, then we will simply call the DFS. Okay, and while coming back from the DFS, after coming back from the DFS, we will update the low of u is equals to the minimum of low of u comma low of v, and if the low of v is greater than the discovery time of u, that means it's a bridge. We will push it into our bridge vector, and that's it. Let's revise. We first initialized our timer, discovery vector, low vector, visited vector, right? Then in DFS we have our node and parent. First we'll mark the node as visited and assign discovery time and low time to timer and increase the timer. Then we will traverse. If the neighboring node is the parent, we will continue. If the neighboring node is already visited, that means there is a cycle found, we will update the low of u, or else we will call the DFS, and after returning back we will check for the condition of the bridges and update the low of u. So what we have studied today is bridges are the edges which on removal will give two separate components of the graph. And in the algorithm we saw, we will perform the DFS. While perform DFS, we will initialize the discovery time and the low time. And when we found a cycle, we will do nothing and trace back, and after returning back, we will update the low of u. And in the successive returning call, we will check for the discovery time of u and low of v, and we will update the low of u in every step as minimum of low of u comma low of v, and we will check for the bridge condition. Right, in the code also we saw the similar thing. While traversal, if the neighboring node is parent, we will continue, or else if the neighboring node is visited, that means cycle found, we will update the low of u, or else we will perform the DFS, and after returning back we will update the low of u and check for the condition of bridge, which is low of v or low of neighboring node should be greater than discovery time of u. So that's it from my side, guys. If you have any questions, please mention them into the comment box, and you find the problem and the solution link into the description box. If you don't understand, don't like, don't subscribe, but if you do, please show some support. Keep practicing, keep smiling. Thank you.